We're solving problem 1 from the 2019 AMC12B. Alicia had 2 containers. The first was 5/6 full of water and the second was empty. She poured all the water from the first container into the second, at which point the second container was 3/4 full of water. What is the ratio of the volume of the first container to the volume of the second container? So we can let A be the volume of the first container and B be the volume of the second container. Then the first is 5/6 of A. And the second one would be 3/4 of B. And since we know that basically no water was lost in the transfer, we say that these are equal because you can't just lose a bunch of water when you're pouring them in between containers. So 5/6 A is 3/4 B. So we want to find A over B, in which we divide both sides by B and then have to multiply both sides by 6/5 times 3/4 is 18 over 20 or 9/10. So that is our answer for this problem. We're solving problem 2 from the 2019 AMC12B. Consider the statement, if n is not prime, then n minus 2 is prime. Which of the following values of n is a counterexample to the statement? So what we could do is we could go about testing the values for all the answer choices because we have 5 of them. But there's some answer choices that won't work because the statement is if n is not prime, then n minus 2 is prime. This means that the first part of the statement, if n is not prime, has to be true, for then the second part of the statement, n minus 2 being prime, to be false. So we need a not prime number that yields a not prime number when you subtract 2 from it. So automatically, answer choices A and C are out because they are prime. Then you can go about testing this one. 15 minus 2 is 13, which is prime. 21 minus 2 is 19, which is prime. 27 minus 2 is 25, so that is our answer choice for this problem. We're solving problem 3 from the 2019 AMC12B. Which one of the following rigid transformations, isometries, maps the line segment AB onto the line segment A prime B prime so that the image of A, -2, 1, is A prime, 2, -1, and the image of B, -1, 4, is B prime, 1, -4. A reflection in the y-axis. B, a counterclockwise rotation around the origin by 90 degrees. C, a translation by 3 units to the right and 5 units down. D, a reflection in the x-axis. Or E, a clockwise rotation about the origin by 180 degrees. So what we can do is one way to do this is just plot it out. So we have 1, 2, 1, that's A. And then for B, we have -1, that's our B. A and B go like that. And then for A prime, it's right over here. And B prime would be right over here. So as you can see, it's definitely not a reflection in the y-axis. It's not a rotation around the origin by 90 degrees, because then it would end up in this quadrant. It's not a translation like this, because then the A and B would be flipped. It's not a reflection in the x-axis either, because then it would look like this. So that's incorrect. So clockwise rotation about origin by 180 degrees. This is the origin, and it goes around here, this way, about 180 degrees, and we see that that is the correct answer, and is the answer for a problem. We're solving problem 4 from the 2019 AMC12B. A positive integer satisfies the equation n plus 1 factorial plus n plus 2, all of this here, it satisfies all of these factorials, and we want to find the sum of the digits of n. So what we can do is these factorials we see all have a factor of n factorial. We just need to factor it out. Now what we can do is we do n plus 1 times n factorial plus, I should just put it on the outside, n plus 2, n plus 1, n factorial is 440 times n factorial. Or no, it's just like that. So all these terms have a factor of n factorial, so then we cancel that out. Then we get n plus 1 plus n plus 2 times n plus 1 is 440. Now, what you can do, multiply this out and subtract 440 from both sides. You get a quadratic, being n squared plus 4n minus 437 is 0. Factoring this, we see that n minus 19 and n plus 23 is a viable simplification. And we have n is positive 19 or negative 23. Now, since the problem states n has to be a positive integer, negative 23 cannot be a solution. So our answer would be 1 plus 9, the sum of the digits of 19, and 1 plus 9 is 10, which is our answer. We're solving problem 5 from the 2019 AMC12B. Each piece of candy in a store costs a whole number of cents. Casper has enough money to buy either 12 pieces of red candy, 14 pieces of green candy, 15 pieces of blue candy, or n pieces of purple candy. A piece of purple candy costs 20 cents. What is the smallest value of n? So, what we do here is, well, we have 12 pieces, 14 pieces, and 15 pieces. To have the smallest value of n, you have to have the least number of, you have to find the LCM for 12, 14, and 15, because that would yield us the least number of money. So we just do LCM of 12, 14, and 15. And by taking out all the prime factors and reorganizing them, by getting the bare bones of this, we get that the LCM of these numbers is 420. So the least number you could have to satisfy the constraint of buying 12 pieces of red candy, 14 pieces of green candy, and 15 pieces of blue candy is to have 420 cents. Now, we know that this number is used to buy 20 cents, so we can find how much a piece of purple candy costs, which is 420 divided by 20, or 21. So that is our answer, 21 pieces of purple candy. We're solving problem 6 from the 2019 AMC12B. In a given plane, points A and B are 10 units apart. How many points C are there in the plane such that the perimeter of triangle ABC is 50 units and the area of triangle ABC is 100 square units? So for this, let's just assume that we have this coordinate plane, and point A is 0, 0, and point B is at 0, or no, 10, 0, for simplicity. So we know that this line has a value of 10. And we know that the perimeter has to be 50 units, and the area has to be 100 square units. So that means the height has to be 20. Point C has to be one of the lines parallel to line AB and 20 units above it, positive 20 or negative 20. Since we want to minimize the perimeter in this case, we have point C to be in the middle of A and B and 20 up, forming a triangle as such, an isosceles. So we can check this because this is minimizing the area, or minimizing the perimeter. So then after that we can just go up and then see if those work. So when we calculate the perimeter, we're gonna have to calculate we're gonna have to calculate these hypotenuses because this is a right angle. So this would be square root 25 plus 20 squared, which is 400, because the height is 20, and the length is 5. Square those and square root it totally. So we get that one of the slanted lengths, or one of these lengths, is square root 425. So hypothetically, two of these lengths, 2 square root 425, plus an additional base length of 10, we would want it to be, well, I mean, we see here, we'd want it to be 50, but obviously, well, I mean, not obviously, but it's not, obviously, because if it was, this would be cleanly 400, yeah, it would be cleanly square root 400, but it's not, and since it's greater, we know that this value is greater than 50. Therefore, there are 0 triangles as such in this formation, and that is our answer. We're solving problem 8 from the 2019 AMC12B. Let f of x be x squared times 1 minus x squared. What is the value of this sum? So the first thing we can do is algebraically manipulate this initial function. So what we can do here is, well, if we just rearrange these, 1 minus x squared times x squared, what we can do with the x squared is actually pretty interesting. This can become 1 minus x all squared, which is still x squared. And we do this because you have the insight to see that this expression would equal f of 1 minus x. So we have now officially proven that f of x is equal to f of 1 minus x. Then applying it to this, we can group it as such. So we do in parentheses f 1 over 2019 minus f of 2018 over 2019, and then plus f of and then we can do just the same thing over here. It would be minus in this case, so negative f 2 over 2019 plus f 2017 over 2019. And you see that if you keep on doing this, it'll end up to f 1009 over 2019, and eventually 1009 over 2019, or hence like the middle numbers, 2019, 1009, 1008, where all of this eventually cancels out to just be 0. So that is our answer for this problem. We're solving problem 9 from the 2019 AMC12B. For how many integral values of x can a triangle of positive area be formed having side lengths log base 2x, log base 4x, and 3? So what we have right here is legs of a triangle, and by the triangle inequality, we know that log base 2 of x plus log base 4 of x is greater than 3. Therefore, solving for x in this case, you get that x is greater than 4. So that's the lower bound. X cannot cannot go below 4 or be of any 4 as a value. Now we need an upper bound, which has to be a power of 2 and 4. And we look at our answer choices, and the closest answer choice that's, we see that it's got to be close in the range of the answer choices, and the closest power of 2 and 4 is 64. So we have 64. Plug into an equation. So we rearrange this one to get 3 plus log base 4 of x is greater than log base 2 of x. We see that 64 does, in this case, work as an upper bound. So the whole inequality is 64 less than x less than 4. So we want to find how many integral lengths. So we do 64 minus 4 minus 1 gives us our answer of 59 integral lengths. We're solving problem 10 from the 2019 AMC12B. The figure below is a map showing 12 cities and 17 roads connecting certain pairs of cities. Paula wishes to travel along exactly 13 of those roads, starting at city A and ending at city L, without traveling along any portion of a road more than once. Paula is allowed to visit a city more than once. How many different routes can Paula take? So we see here that we have this route, and we can just construct an example route. We know that some of the edges, we know that exactly 4 edges are not going to be used because Paula wishes to travel exactly 13 of the roads, and there are 17 roads in total. So what we can do is we construct an example path. She starts at A, walks here, so therefore she doesn't use this one or this one. The X's represents roads she doesn't use. Now at this first point, she faces a choice. She can either go forward and double back later, or she can go and make a loop. So if so these are intersection points, call them O or something, because they have 2 choices you can make. If she chooses to make a loop, she goes like this, this, and then goes this way to the second O over here, where again she can either go forward or make a loop. Or when you go forward and then turn back to later, or you could go in a loop. So if you go in a loop again, here, 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 and then only way you can get out is from here and here. She then uses these 2 unused edges. So what we really have here is a description of how this should work. So since we have 2 of these O's, which means an O is a part of a road, or like an end of a road, where you can make 2 choices to get to 13. So we have one part of 2 choices and another 2 choices you can make. So you can have a total of 4 different routes taken to get from city A to city L, and 13 roads taken. We're solving problem 11 from the 2019 AMC12B. How many unordered pairs of edges of a given cube determine a plane? So let's just first draw a cube. So a cube has 6 faces, and this is just going to be a really rough drawing. So we want to find how much ways we can select select an edge and then make a plane with other edges. So we know that there are in a cube 12 total edges. If you select any one edge, say this one with the I'm gonna show it with the squiggly line, how many more edges can form a plane? Well, you can use this one, that's this one, this one, this one, that one behind, that one there, and so far that is 6. 1, 2, 3, 4, 5, 6. But we can also use this plane, we can also use this edge to make a diagonal plane. So that's in total 7. So for any given edge, we can use 7 other edges to form a plane. So we have 7, and multiplied by the total number of edges is 84. But we overcounted because we're doing 7 times 12 times is 84. We have 7 of the 12 edges being selected for one edge. But we have to compensate for when 2 edges are selected and then selected again, but in the reverse order. So if you could say this one is selected and that one's selected, that would be one pairing. So this edge and that edge would be a pair, but we also count this edge and that edge. So like if you say this edge is A and this edge is B, you'd count A and B, but also B and A. So you overcount by multiplying it by 2. So you have to divide 84 by 2 to get our answer, which is 42. There are 42 ways to do this. We're solving problem 12 from the 2019 AMC12B. Right triangle ACD with right angle at C is constructed outwards on the hypotenuse AC of isosceles right triangle ABC with leg length 1 as shown, so that the two triangles have equal perimeters. What is sine of 2BAD? So first thing we see is that triangle ABC is a right triangle, and both AB and BC are equal to 1. Therefore, this is a 45-45-90 triangle, which means that the hypotenuse, or AC, is equal to the square root of 2. Since we know that they have equal perimeters, what we can do is, we know that AC is a side that both of these triangles have. So we can just take away the side of AC to sum BC and BA to be 2. And then if we take away AC, then we get that CD plus DA is also equal to 2. Then we can apply the Pythagorean theorem on this second triangle. So we get AC squared plus CD squared. AC squared is square root 2 squared, and then this CD squared will be from here 2 minus DA squared equals the hypotenuse, or DA squared. All this becomes 2 plus 4 minus 4DA plus DA squared equals DA squared. So these cancel, and DA is equal to 3 over 2. So what we can do now is, since we know that DA is 3 over 2, and DA and CD have to sum to 2, then CD has to be 1/2, because then 3/2 plus 1/2 is 2. So what we can do now is we can start solving for this angle. So we let angle theta be angle DAC. hence this angle on this triangle, theta. Now, what we want to solve for is, we want to eventually solve for sine of 90 degrees plus 2 theta. This simplifies to cosine of 2 theta. We know that cosine of theta, in this case, will be 2 root 2 over 3 by solving. So it's easy, we can compute cosine of 2 theta, which is 2 of 8/9 minus 1, which is 7 over 9, which is going to be our answer for this problem. We're solving problem 13 from the 2019 AMC 12B. A red ball and a green ball are randomly and independently tossed into bins numbered with the positive integers, so that for each ball, the probability that it is tossed into bin k is 2 to the power of negative k for k equals 1, 2, 3, ... What is the probability that the red ball is tossed into a higher numbered bin than the green ball? So if we have probability to negative k, for k being positive, all positive integers, well, we can just sort of list out the probabilities. So this would be 1/2, 1/4, 1/8, and 1/16, and so forth. All we can do here is, well, we can, in order for the red ball to get tossed into a higher numbered bin than the green ball, what we can do is we remove all the probabilities where k is odd, because if we have all the even numbers, that's all the successes we want. Because even if you have like a ball that a green lands in that's like odd, even if it lands in an odd bin, the red one can always go one further into an even. So this becomes 1/4, 1/16, 1/64, and so forth. We then want to find the sum of these probabilities. So we can do fancy calculus stuff. So you do sum I is 1 to infinity, because this is a sequence that goes to infinity, and it's the equation simply 1/4 to the power of I, which is 1/3. And that is our answer for this problem. We're solving problem 14 from the 2019 AMC 12B. Let S be the set of all positive integer divisors of 100,000. How many numbers are the product of two distinct elements of S? So we have 100,000. And this can be factored into 2 to the power of 5 times 5 to the power of 5. Now, right now, when we see divisors, the word divisors, you can probably immediately jump to calculating the divisor, or the amount of divisors. So, in the set S, we have 5 plus 1 times 5 plus 1, which is 36 numbers in set S, because that's 36 divisors. And this is through the divisor formula, where you get by prime factorizing a number and multiplying the powers together, but add 1 inside the parentheses. So we have 36 elements in S. Now, if you have the number 5 to the power of n, this yields, it ends in 5. It ends in 5. It always just ends in 5. That's a clear characteristic of being a multiple of 5. However, if you have a multiple of 2 or a power of 2, well, you can have 4 values: 2, 4, 8, and 6. It ends in any of these numbers, but you account for the powers of 0, and then you get and then you can also get 0 henceforth and 1. So total set would be 0, 1, 2, 4, 5, 6, 8. But most divisors, most of them, basically, they either just end in 0, 1, or 5. And since these are all these, you multiply 3 of the what it ends in by 36, which yields 108. And you have 3 of these numbers split into 2 to the power of n's and 2 to the power of zeros. So 3 squared is 9, and then you add 9 to the total. So 108 plus 9 is 117, and that is our answer for this problem. There are 117 numbers that are the product of 2 distinct elements of S. We're solving problem 15 from the 2019 AMC12B. As shown in the figure, line segment AD is trisected by points B and C, so that AB equals BC equals CD equals 2. 3 semicircles of radius 1, AEB, BFC, and CGD have their diameters on AD and are tangent to line EG at E, F, and G respectively. A circle of radius 2 has its center on F. The area of the region inside the circle but outside the 3 semicircles can be expressed in the form A over B times pi minus root C plus D, where A, B, C, and D are positive integers and A and B are relatively prime. What is A plus B plus C plus D? So for this problem, what we can do is we can sort of find smaller portions of the total area. So we have this giant circle, and since F is the center, we know that this upper part is the upper half of the circle. So we can just set that as area A. I know it already says variable A in this problem, but we're not really going to be using it that much. And then these dotted lines that I drew from F extending to these 2 points, well, we know that this entire arc length is 120 degrees because it forms a 30, 60, 90 triangle here. Because this is 1 and that is 2, 30, 60, 90, and then 60 times 2 is 120. So we have that, called all that area the arc B, and then, well, we have the arc. So if we sum this plus the arc, we'd be including this part, this middle semicircle. So we have to subtract that. And what better way to do that is when you subtract this entire top triangle and call that triangle C. So now you just have this lower part and this upper part. All you need to do is to sum these weird looking thingies, the things you get when you inscribe a circle and a square and it's on the corners. So like if you have a circle, So basically what those are is where you have like a square and then inscribe a circle in it. These are the gaps in the corners. It's what it is. So those gaps, there's 2 of them. We call them that D. So it's pretty intuitive to solve for area A. Area A is simply 1/2 pi times 2 squared, which is 2 pi. Area B is an arc, so 120 degrees over 360 degrees, pi times 2 squared is 4 pi over 3. For area C, the big triangle is basically just 2 30, 60, 90 triangles, where we know that the height is 1 because the radius of the semicircles is 1. Then we have, this is 2 times 1/2 times, we have root 3 as the longer length because that is part of the 30, 60, 90 triangle rules times 1. And this simply gets you to root 3. So for area D, the corners, we have 4 times 1, and then you have to subtract 1/4 pi times 2 squared, so, or 4 minus pi. And what you want to do algebraically is you add A, B, subtract C, because we don't want this semicircle, and then add D. So by applying this over here with these values, we have 2 pi plus 4 pi over 3 plus root 3 plus 4 minus pi. So this all gets you to 7 pi over 3. Oh, wait, no, because you subtract this. So you subtract this minus root 3 and then plus 4. So we've now expressed the area of the unshaded region in this form. Then we can add A, B, C, and D. So 7 plus 3 plus 3 plus 4 is 17, and that's our answer for this problem. We're solving problem 16 from the 2019 AMC12B. There are lily pads in a row numbered 0 to 11 in that order. There are predators on lily pads 3 and 6, and a morsel of food on lily pad 10. Fiona the frog starts on pad 0, and from any given lily pad has a 1/2 chance to hop onto the next pad and an equal chance to jump 2 pads. What is the probability that Fiona reaches pad 10 without landing on either pad 3 or pad 6? So we can just draw these out as like circles. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 12 pads here. So this is the one she starts with. Let's just say F for Fiona. And there's predators on lily pads 3 and 6. 1, 2, 3. Let's mark that with an X. And then another 1, 2, 3, another X. And then for 10, 7, 8, 9, 10, that's food. So I'm just going to put a check mark there. So what we see is that, well, in order to get past the predators on 3 and 6, Fiona has to land on lily pads 4 and 7 respectively, because she can only jump 2 pads at a time. So the only way she can get past is if she jumps 2 pads from the pad before the pad with a predator to get to the one right next to it. So we would have, since there's a predator on 3, she'd have to be at 4 in order to get past, and since there's a predator on 6, she'd have to be at 7. So we also see that when Fiona gets past 6, we see that we can break this entire puzzle into 3 sections. This section, the 7 to 10, 6 to 4, and 0 to 3. So we see that these two, 0 to 3 and 7 to 10, are complements of each other, because basically whatever this probability is, this probability is going to be 1 minus that probability, because they all have a distance of a total of 4 pads, but this one, she's not going on the 4th one, and this one, she is going on the 4th one. So we have that. So we can start just solving for the first one. In order to get in order to get past this and land on here, Fiona can either jump once again, and jump twice, or jump twice and jump twice 2 times. This yields 1/4 probability, and this one yields 1/8. So when you sum these two, 1/8 plus 1/4 is 3/8, which is our total probability that she gets past the first predator. And now she's over here. Now, for this second case, there's only one way she can do this, where she jumps one time, she jumps one time, or she jumps once, and then just jumps 2 times, so this is 1/4 probability. Now, since this is the complement of that, basically what this means is that they're both in the same, like they both have 4 lily pads, but this one has a probability of 3/8 on not landing on this one. So therefore, this will have a probability of 1 minus 3/8 or 5/8 of landing on lily pad number 10. And since these are all independent events, we multiply them together to get our total probability, which is going to be 15/256, which is our answer for this problem. We're solving problem 17 from the 2019 AMC12B. How many non-zero complex numbers z have the property that 0, z, and z cubed, when represented by points in the complex plane, are the 3 distinct vertices of an equilateral triangle? So what we can first do is we say that the complex number z is equal to r cis theta, where r and theta are both real numbers. Then we use De Moivre's theorem, gives us z cubed, I don't like that thingy in the middle, z cubed is r cubed cis of 3 theta. So we have this right here, and basically, since we have we have this, we want to find how many non-zero complex numbers z have this property. And well, first thing we see is that since it's an equilateral triangle, 3 distinct vertices of an equilateral triangle, well, an equilateral triangle has 3 equal sides. So therefore, lengths must be equal. So what this basically means is that the distance from 0 to z has to equal this distance from 0 to z cubed, meaning that r cubed is equal to r, so then r is equal to 1. Then we plug that into this, z cubed equals cis of 3 theta. So we have now cis 3 theta divide cis theta. This is cis of 2 theta, which is cis of plus minus pi over 3. Now this is important. Since we know that this inequality is true, then what this basically means is that this loops around 2 times in a circle, and plus or minus pi over 3 is 2 points. So since it loops around 2 times in 2 points, 2 times 2 is 4, so we just have 4. And that is our answer for non-zero complex numbers z. We're solving problem 18 from the 2019 AMC12B. Square pyramid ABCDE has base ABCD, which measures 3 centimeters on a side, and altitude AE perpendicular to the base, which measures 6 centimeters. Point P lies on BE 1/3 of the way from B to E. Point Q lies on DE 1/3 of the way from D to E, and point R lies on CE 2/3 of the way from C to E. What is the area in square centimeters of triangle PEQR? Now, what we have here is a bird's eye view of this square pyramid. where we have set coordinates for A, B, C, D, and E in the X, Y, and Z plane. We can now start calculating the coordinates for P, Q, and R, which are shown like this in a bird's eye view from looking at the top. P has coordinates, well, from this we see that the X direction is 2, Y direction is 0, and Z, well, it says P is 1/3 of the way from B to E. And since we know that the altitude AE is 6, 1/3 of 6 is 2. So our Z coordinate is 2. We have Q, which is 0, 2, and then our Z coordinate. It's also 1/3 of the way from D to E. So again, 1/3 of 6 is 2. And then R. We have 1, 1, 1 for the X and Y, and for the Z, it says point R is 2/3 of the way from C to E. So 2/3 of 6 is 4. So now we have these new coordinates. We know that PQ is coordinate to this, is length PQ is parallel to this base here. So what we can do is, well, we can basically just apply the distance formula. So what we can do is we have the distance of this, which is just this triangle here, right triangle, and then we have 2 squared plus 2 squared, square rooted, is equal to, this is 8, square root of 8 is simplified to 2 root 2. And then the height, for the height, what we can do is, that's just the highest point, which is R, and then subtract from Q, which is 4 minus 2, or 2. So the height is 2. Then we can solve for the area of the triangle. So we have 1/2 times 2 root 2 times 2. That cancels out. And our area is simply 2 root 2. And that is our answer for this problem. We're solving problem 19 from the 2019 AMC12B. Rashawn, Sylvia, and Ted play the following game. Each person starts with $1. A bell rings every 15 seconds, at which time each of the players who currently have money simultaneously chooses one of the other 2 players independently and at random and gives $1 to that player. What is the probability that after the bell is rung 2019 times, each player will have $1? So, let's just denote our starting position as 1, 1, 1. We have Rashawn, Sylvia, and Ted. So, we can just start playing this game. What we can do is, if we want to stay in where the case where each person has $1, that means 1, 1, 1. We'd have to do R gives his $1 to S, S gives his $1 to T, and T gives his $1 to R. This can also be done in another way. R to T, T to S, S to R. So there are 2 total ways to stay in the position where each person has $1. And the total number of ways people can do this, the total number of ways they can distribute the money is, each person has 2 choices, the other people, and it's multiplied by 3. It's cubed because there are 3 people, hence these 3 people are making this each have 2 outcomes. So this is 8. So then we have 2 over 8 is 1/4. So we have 1/4 of probability if you come from this and go to that. However, there's also another configuration, and this is the only other configuration. It's where someone has $2, one has 1, and someone has 0. Let's say Rashawn is the one that has $2, Sylvia is the one that has $1, and Ted has $0. To get back to 1, 1, 1, what you're gonna have to do, well, let's just first to do this, we see that Rashawn has to give his dollar to Sylvia, and Sylvia has to give her a dollar to Ted. And then there are, in this case, 2 squared, because Ted cannot participate since he does not have a dollar, which is 4. So this is only one configuration out of 4 total, and again, 1/4 probability. Since these are the only 2 configurations as a configuration where one person has $3 is impossible because you can't give money to yourself. These are the only 2 configurations, and each of them have probability 1/4. So no matter which state we are in the 2018 ring, it will both have an equal probability of 1/4 for both cases to return back to its original 1-1-1 configuration. We're solving problem 20 from the 2019 AMC12B. Points A, 6, 13, and B, 12, 11 lie on circle omega in the plane. Suppose that the tangent lines to omega at A and B intersect at a point on the x-axis. What is the area of omega? So we have these 2 points plotted, and we know that they're on a circle, so we can just like sketch that they're on a circle. My drawing is not very accurate because I don't have any tools to assist me. There you go. There, about, and then, well, we know that there's gotta be some point on the x-axis that both of the lines intersect. So we know that these lines are equal in length. So what we can do is just call that point that both lines intersect on is x, 0. What we can do now is apply the Pythagorean theorem using points A and B. So by doing that, we get square root x minus 6 squared plus 13 squared is equal to the square root of x minus 12 squared plus 11 squared. Square rooted all of that. And once you evaluate this, because this is 169 and that is 121, you eventually get that x equals 5. Then our unknown point becomes 5, 0. So 1, 2, 3, 4, 5, find that point, and we just draw really rough lines, and we know they go past this circle, and they also go like past that. So that's our point A, B, O. Call that x, and right now what we can do, draw this line from O to x, and we have this new center over here, O prime, because we see that quadrilateral AOBX is cyclic, and this is probably due to my really bad drawing skills, but this is supposed to be curved inward more, but it's supposed to be cyclic around that line because O prime is the center of this circle, just very about. So we have that. So now we know that quadrilateral AOBX is cyclic. We can apply Ptolemy's theorem, and that yields us 2 root 170 times r is equal to d times square root 40. Now you might be thinking, where'd you get these new variables from, r and d? Well, r we set as the radius of the circle, and d is the distance from the center to 0.5, 0. Then we can apply the Pythagorean theorem so that 170 plus r squared is equal to 17 r squared. This gives us r squared is 85 over 8. So then all we have to do is add in pi to get the area. So the area is 85 pi over 8. And that is our answer for this problem. We're solving problem 21 from the 2019 AMC12B. How many quadratic polynomials with real coefficients are there such that the set of roots equals the set of coefficients? For clarification, if the polynomial is ax squared plus bx plus c is not equal to 0, and the roots are r and s, then this is the requirement. So we see here that if r is s and a equals b equals c, then this equation becomes this equation. Then we can start considering the cases. For case number 1, what we would have is a is b is r, and c is s, but not r. Then this equation simplifies to ax squared plus ax plus c is equal to 0. We can apply Vieta's formulas here. So a plus c is equal to -1. A times c is equal to c over a. Is that ac? No, ac. No, I'm pretty sure it's -1. So what we have here now, we already see that if c is equal to 0 is -1, this equation becomes -x squared minus x equals 0, which is for first valid solution. Then this equation simplifies to a squared minus 1c equals 0. And if c is not 0, then a squared minus 1 is 0, giving us that a is plus or minus 1. If a equals 1, c is -2, so then this equation becomes x squared minus plus x minus 2 is 0. Second valid solution. Then what we can do, case 2, is we have a equals c equals r, b is s, not equal to r. We have ax squared plus bx plus a equals 0. And what we can do is we use Vieta's formulas again. A plus b equals -b over a. B is simply ab simply just simplifies down to 1. So we see here there's only one solution, where we have a cubed plus a plus 1. That's like the only one that works if it goes in. So we have yet another one for this. So that's our third. That's our third valid quadratic polynomial. Case 3, we have a equals r, b equals c equals s, which is not equal to r. Then we'd have ax squared plus bx plus b is equal to 0. What we have here now, we again apply Vieta's formulas. A plus b equals -b over a. AB is positive b over a. And then from this equation, a is 1 over a, so a is plus or minus 1. If a is 1, positive 1, then 1 plus b equals negative b, which yields b as negative 1/2. Plugging it into this form equation, we get x squared minus 1/2 x minus 1/2 equals 0, which is our fourth valid solution. If we do a equals negative 1, however, 1 plus b is equal to b. That's not true. That can never be true. So a equals negative 1 is not a solution, leaving us with only 4 quadratic polynomials for this problem as our answer. We're solving problem 22 from the 2019 AMC12B. Define a sequence recursively by x0 is 5, and this to be true for all non-negative integers n. Let n be the least positive integer such that this is true, and we need to find in which of the following intervals does n lie. So the first thing we can do is simplify this into this. Now what we can do is we let x of n be 4 plus number f of n. Then, when we subtract this x of n, xn plus 1 minus xn is 4 minus x of n over, oh no, this is just f of n over this. The denominator simplifies to 10 plus f of n, which when we're rounding, we round to f of n over 10. Now, the desired outcome is for m to be like this, and the lowest, x sub 0, is equal to 4 plus 1 over 2 to the power of 2 to the power of 0. So then we can set x j to be equal to 4 plus 1 over 2 to the power of I, so that f of j is 1 over 2 to the power of I. X sub k is 4 plus 1 over 2 I plus 1. F of k is 1 over 2 I plus 1. Then we get x sub j minus x sub k is equal to 1 over 2 I plus 1, which is approximately f of n over 10 plus f of j plus 1 over 10 plus all the way to f of k minus 1 over 10. Now we know that 1 over 2 to the power of I. Also, by the way, this might be too late to be saying this, but from this we see that this is a decreasing equation. X of n is decreasing, and can never go below 5. 5 is like basically the constraint here. So now we know that 1 over 2 to the power of I, which is equal to f of j, it's greater than f of j plus 1, greater than f of j plus 2, all the way, so that lowest term, f k minus 1, f k, which is 1 over 2 to the power of I plus 1. So we've calculated this. Now we do k minus j times 1 over 2 to the power of I over 10. We know that this is less than or greater than this has got to be 1 f sub j over 10 plus f sub j plus 1 over 10 ... all the way to f sub k minus 1 over 10 and the term over here is k minus j times 1 over 2 I plus 1 over 10. Therefore, k minus j lie in this interval. So by deducting some further work, we see that interval, does m lie? It lies in the interval C, since they're all pretty far apart intervals, which is 81 to 242, and that is our answer for this problem. This is solution 2 of problem 22 for the 2019 AMC12B. So for this solution, we do the same thing. We simplify this over, realize that x sub n is decreasing, subtract this, so we get xn plus 1 minus x sub n is 4 minus x sub n, and then do the same thing as before. Denominator becomes 10. Then we see that xn plus 1 is 9/5, 9/10 n, x of n plus 2 over 5. Since we see that this is the desired x sub m, we know that we want, so if we eventually have xn plus 1 is 4 plus 9/10 xn, we want, it ends up like this, so we'd want this expression to be equaling this expression right there. So then we can just do that using logs. 9 over 10 power of n equals 1 over 2 to the power of 20. You can just approximately calculate, you calculate this using the logs. N is like 120-ish. But we see that the answer choices, the intervals are relatively large, and if you get a number around here, it's clearly in the interval C, which is 81 to 42, which is our answer for this problem. We're solving problem 23 from the 2019 AMC12B. How many sequences of zeros and ones of length 19 are there that begin with a 0, end with a 0, contain no 2 consecutive zeros, and contain no 3 consecutive ones? So we know that this ends in a 0. Whatever it is ends in a 0. And it says it cannot contain 2 consecutive zeros. So the term before that, the second to last term, has to be a 1. And now this is where things branch off. There's 2 cases. One where the next number is 0, or one where the next number is 1. If the third to last number is 1, we cannot have 3 consecutive zeros, as the problem says. So therefore, this has to be, this fourth, has to be a 0. So we see that zeros either repeat themselves two digits away or 3 digits away. So they are basically composed like this. So what we can do now is we can just we realize this, so we know that it starts with a 0, ends with a 0. So we're counting 18, and we know that a sequence of 2s and 3s have to sum up to 18. So what we can do is we can just start counting. For one of our case, we have, if we just have 9 2s, that's a valid case. Gets us one way. Second way, we have 2 3s, that's 6, and 6 2s. That gets us 6 plus 12, which is 18, and this is 8, choose 5, or 28 ways. 3 is going to be 3 2s, and 4 3s, giving us 7 choose 4, 35 ways. And the final way you can make it add up to 18 with only 2s and 3s is if you just do 6 3s. This is just 1. So our total sum, 1 plus 28 plus 35 plus 1, gives us our answer of 65, and we are done. The second way to do this is more algebraically, in my opinion, but you first notice that we still have the repeating zeros, either 2 or 3 digits away. So we can denote it as f of n, the total number of digits, is basically composed of n minus 2s and n minus 3s, so they're composed of zeros 2 and 3 units away. So we have this. Now we can start just like doing these calculations by hand. They're pretty simple, I'd say. So it starts at f of 3, 1, f of 4, 1, f of 5, 1, f of 6, 1 plus 1 is 2, f of 7, 1 plus 1 is 2, f of 8 is 1 plus 2 or 3, and so on and so forth. Now now you get, for the last two terms, you should get f of 18 is, because we're doing this for all 19 of them, all 19 digits. So f sub 18 is 21 plus 28 is 49. F of 19, that's 9. F of 19 is 28 plus 37, which is 65. Again, our answer for this problem. We're solving problem 24 from the 2019 AMC 12B. Let omega be equal to all this. Let S denote all points in the complex plane of the form a plus b omega plus c omega squared, where 0 is less than or equal to a, is less than or equal to 1, 0 is less than or equal to b, less than or equal to 1, and c is greater than or equal to 0, less than or equal to 1. What is the area of S? So for this problem, what we can do is we can find the possible values for these terms. The possible values for c omega squared would be c times -1/2 minus root 3 over 2 times I. And so what it's starting to look like, it could be looking like this, just like a stick going out there. For every one of these points, you add beta omega, which is beta -1/2 plus root 3 over 2 times I. So now you get to add all of this. So we get 2 equilateral triangles. And then we add more points on this for the A part in order to eventually form a hexagon, a regular hexagon, in fact, with side length 1. And we can simply calculate the area of this hexagon to be 3 over 2 root 3, and that is our answer for this problem. We're solving problem 25 from the 2019 AMC 12B. Let ABCD be a convex quadrilateral with BC equals 2 and CD equals 6. Suppose that the centroids of triangle ABC, triangle BCD, and triangle ACD form the vertices of an equilateral triangle. What is the maximum possible value of the area of ABCD? So
what we can do is we draw a bunch of these lines, where these lines that are on a line, not from a point or a vertice. They are at the exact halfway mark, although it's not really drawn to scale. And what we get is these 3 points, x, y, and z. And what we notice is that when we put in the centroids, when we put in the centroids, call them G1, G2, G3, we see that G1, G2, and G3 are 2/3 of the way from C to points x, y, and z respectively for the 3 triangles ABD, ABC, and BCD. So what this basically shows is that triangle ABD is an equilateral triangle. And the formula for the area of an equilateral triangle is s squared root 3 over 4. What we can do is we can now use this angle to use the law of cosines on triangle BCD, because we have 2 of the side lengths, to solve for BD, which is an edge of the equilateral triangle ABD. So s squared is, we just use the law of cosines, 2 squared plus 6 squared minus 2 times 6 cosine. That angle, BCD, call that theta. We get that s is equal to square root 4 plus 36 minus 24 cosine theta. This is basically just 40. We plug it into this, so the area of ABD, I'll just do it like this. The area is equal to square root 40 minus 24 cosine theta squared root 3 over 4. So this square root is just gone, leaving the area to be equal to 10 minus 6 root 3 cosine theta. And we get the area of triangle BCD by using another area formula with trig. So we use the sine formula since we get 2 sides of the triangle and we have an unknown angle. So then what we can do is we know that triangle BCD is equal to 1/2 times 2 times 6 times sine theta, which is 6 sine theta. So total area, then I'll just denote it by A. This is 10 root 3, by the way, is 10 root 3 minus 6 root 3 cosine theta plus 6 sine theta. We can factor out a 6 from this to get 10 root 3 plus 6 sine theta minus root 3 cosine theta, which is 10 root 3 plus 12 sine of theta minus 60. So we know that this value right here has to be less than or equal to 10 root 3 plus 12. And this is the greatest value of 12 sine theta minus 60, because the greatest value of sine is 1. So this would be our greatest area for this problem and is our desired area. We're solving problem 25 from the 2019 AMC12B. This is solution 2. For this solution, what we can do is we see that the centroids of the 3 triangles, the centroids would be first, to find the centroids, in an algebraic notation, we can correlate all these points to lowercase letters. So denote point A to be A, lowercase point uppercase b to be lowercase b, and so on. Therefore, the centroids of these three triangles would be A plus B plus C over 3, B plus C plus D over 3, and A plus C plus D over 3. The pairwise distances between the centroids would then be the absolute value of D minus A over 3, absolute value of B minus A over 3, and the absolute value of B minus D over 3. And note that all of these are equal. If these are equal, then that means that absolute value of D minus A is equal to the absolute value of B minus A is equal to the absolute value of B minus D. Then this proves that triangle ABD is equilateral, and then we can go down the same process of the last solution by solving for a side length using the law of cosines, and then finding the area of this triangle using the sine triangle area formula, and then to eventually get maximum area is 10 root 3 plus 12. So again, we get our answer.